So we are going to look at this phase plane. So this phase plane comes, is it not showing? Come on, air server. This phase plane that is now on the screen. So this phase plane is from the differential equation x prime equals negative x minus y times 1 minus x minus y, and y prime, which equals x times 2 plus y. And then if you were to solve this, it would have the following critical points. We would have 0, 0, 0, 1, negative 2, negative 2, and 3, negative 2. I want to focus on the 0, 1 critical point. So if we look at the 0, 1 critical point, what do you notice about it? Besides that I've shaded it kind of strangely. It's not going to be a center because you can see those blue lines are actually getting towards it. They are spiraling, but they are actually going to reach the point. So it is a spiral node is what we called it. So we've got 0, 1. This is going to be an asymptotically stable node. So the natural question to ask ourselves is what initial conditions are going to lead us to a point where that solution with that initial condition is going to approach that critical point, right? So if you are in this area where you are going to approach that critical point, if you start there, that is called your basin of attraction. So the blue shaded region on this. So any initial condition that I take in this case, I'm eventually going to be approaching that critical point. And then your separatrix, that's how I'm going to pronounce it, separatrix, is that trajectory that is separating the points that are attracted to that critical. They're the trajectories that are attracted to the critical point from the ones that aren't. So in this case, it's the outside of this basin, right? If you were to follow that trajectory, you wouldn't actually go to the critical point, and anything outside of that is moving away from that critical point, potentially to one of your other critical points or just off towards infinity, depending on the differential system that you're looking at. So that separatrix is the separation of the basin from the rest.
Like on a back horizon?
Yes. Okay. Okay. Any questions about that? So I think that's just really cool. It's one of those ways, because remember, this whole section is about qualitatively describing our differential equations. So based on this, you could be like any initial condition, let's say, what would be in here? It looks like 1, 0 would be in here. If you had that initial condition from your solution, you would go towards this critical point. But if you had 3, 0, you would not be moving towards that critical point. So it gives you some more information about the behavior of your differential equation depending on your initial condition. So the last thing I want to talk about today is like, well, how can we actually find these trajectories? Because there are times that we can find the trajectories. So how to find trajectories. Okay. So let's let dx dt be capital F of x comma y, and then dy dt be capital G of x comma y. We are going to set up a new differential equation. So we are going to look at dy dx, which is just G over F, which works because if you were to like write dy dt over dx dt, those dt's would cancel. And to find our trajectories, we are going to solve this new differential equation. If possible. It's clearly not always going to be possible, but can we do it? So let's just look at a really easy example. Let's say that dx dt is y and dy dt is x. So for my new differential equation, I'm going to have dy dx equals x over y. Okay. How do you want me to solve this differential equation? Separation of variables, I love it. So I've got y dy equals x dx. If I integrate both sides, I'm going to get 1/2 y squared equals 1/2 x squared plus c. But I personally do not want to deal with these 1/2s. So I'm going to get rid of them by multiplying both sides by 2, which gives me y squared equals x squared plus c. And now I'm actually going to solve this equation for c. When I solve this equation for c, I get y squared minus x squared equals c. And then to get my trajectories, I can graph this for different values of c. Okay. Does anybody happen to know what this graph looks like? It's not a circle. It would be if it was a plus. Nope, not an ellipse. Still a plus. It's a hyperbola. Or hyperbola or hyperbolic paraboloid. I can't remember the difference. It's this. So, right, these are for different values of c. So this is probably a larger c value. A larger c value, we would get maybe this and this. But if we do it for all these c values, we get all these different trajectories. And then let's go ahead and see what this is phase plane would look like. Fine. Same thing. So it's just a way for you to figure out all those different trajectories. Now, is it reasonable to always be able to solve that differential equation? No, but like the whole point of this exercise is we're like, these are hard differential equations to solve. Let's instead look at pretty pictures. So, yeah. All right. So last problem on your in-class assignment. I didn't give you a problem. I didn't get an equation, and I don't remember which one. I went back in my notes and tried to figure out which one. I like didn't press sync or something. I don't know. So we're not going to worry about it. We're going to call it a day for now. I will let Dr. Thomas know that we were confused on what we were supposed to be doing on that problem. And she is teaching next week, so I'll kind of put that ball in her court and let her decide how she wants to handle that. Yeah. Any questions for me? I love it. Thank you. I'm always looking for some artistic flair. All right. If you guys want to turn in your class assignments, I'm happy to take them. Otherwise, I will make it a point to come Monday, first thing at 5. Okay. Thank you. Thank you. Great. This is, yeah. Okay. I had to panic for a second, but I hadn't, we were meeting Friday and I hadn't prepared enough material, but. Yes.
Yeah,
We're gonna have so. It's like the best one. You're welcome. Need to ground. Yeah.
Well, so I got x equals 2 and y equals x.
Great. So when x equals 2, what does y have to be? Using
2.
this equation.
Well, y could be anything. Oh, with x is here.
Well, if x is 2, you're going to get
0, 4, -4.
Yeah. So what does y have to be?
0.
0, right? Because if this is not 0, this has to be because they multiply to give you 0, right?
Yes.
So you've got the point 0. Sorry, you've got the point 2 and 0, right? So that's one of your points. Okay. And now we need to deal with why we need to deal with this equation. So do you want to substitute in y or do you want to substitute, like, we have to substitute something in here. What do you want to substitute in?
Y equals x.
Okay.
X is
So we're at
2x minus x squared minus x cubed.
yes, that is true, but probably to solve this, I'm going to factor out a negative x because whenever I'm trying to solve a quadratic, I really prefer having my x here. So we have x squared, but that gives me x squared plus x minus 2, changing all those signs.
Yes.
Okay. How are you going to solve this? Well, I guess you're going to get 2 answers. One of your answers is x equals 0. So we're going to get the point 0, 0. Well, x equals 0, and we got that from y equals x. So that means y also has to be 0, right?
Yes.
Okay. So now I want to solve this other thing.
From inspection, it's going to be +2 and -1. No. Yes.
Yeah. So +2 and -1. I love that. So x equals, well, I guess we'd have x plus 2 times x minus 1 equals 0. Yeah.
Yes.
So
-2, +1.
Yep. And then what y values go with these points?
That would be -2 and +1.
Great.
Okay. Thank you.